Afternoon to all of you. It's for me a great pleasure to present Amaury Hayat, our first speaker this year. So by the way, we wish you all the best for 2024. In this series of lectures in which we try to bring different experts on the various areas and directions on the interface between mathematics, artificial intelligence as one of the goals of the Center MoD, Mathematics of Data of FAU. We thought that Amaury Hayat could be a very appropriate speaker. Amaury, he's at present professor in the École de Ponts, the bridges school in Cernix, near Paris.
Paris.
Is Marne-la-Vallée?
It's actually exactly half between Paris and Marne-la-Vallée.
Okay, yeah. So southeast of Paris. And so Amaury is now professor in École de Ponts. He was previously a student in École Polytechnique, in the predecessor's École Polytechnique of Paris, of France, actually. And then soon after finishing his studies in Polytechnique, he wrote a PhD thesis with Jean-Michel Coron in Sorbonne University in Paris. And he has developed several expertises, and this is why we thought he could be a good speaker for this seminar series. One of them is, say, core applied mathematics, hyperbolic systems motivated by different kind of applications like traffic and fluid mechanics, and then control, stabilization, backstepping for these hyperbolic systems. That's, say, from the pure analysis perspective. He was also engaged in some very interesting applications of this theory in collaboration with some people here, like the team of Flug and also Alex Kaima, that are collaborating also with Benedetto Piccoli in Rutgers University and Pennsylvania and some other groups on trying to understand to which extent these ideas can be really implemented in order to regulate traffic. The controllers being in those cases autonomous cars. And I remember seeing his habilitation thesis recently, and I like very much this, say, first hint of, really running the experiments to see somehow, evidences to be able to measure, take, really calibrate the validity of the predictions done by the mathematical analysis of these models. And I also like a lot this idea that, well, once you have done the experiment, you can do one step further. And then rather than, using control laws that are designed and computed analytically by mathematical methods, just, let them to be discovered to artificial intelligence. I don't know whether you are doing it with ChatGPT or what. I mean, you can tell us later, right? But it would be like saying, okay, so, rather than writing the exam, say, okay, so ChatGPT, please do it for me, right? Take the risk. And so these three avenues of work that he's merging in his research agenda, I found that particularly interesting. And I think this is more or less the spirit of his talk, whose title is The Role of Artificial Intelligence in the Future of Mathematics. So we are particularly delighted that you accepted our invitation, and well, we hope to see you soon again. Hopefully next time there will not be any strike on trains, so you can do it right. Otherwise, we have also the e-bike. That's a good alternative. Very good.
Thank you very much. Thank you very much, Enrique. It's a great pleasure to be in Erlangen today. I'm very happy to be in this amazing place. It's also a great privilege to be able to give the first MoD lecture of the year 2024. And when Professor Enrique Zuazo invited me last November, the two previous speakers were Lagrange Prize laureate and a Fields medalist. So this is either a very high bar or the beginning of a very long joke. So I think the reason I'm here today is because I love mathematics. I love its complexity. I love the kind of creativity you need in mathematics. But I love also the fact that the more you study it, the more you start seeing things appearing that you hadn't seen before. And this is the reason why when a few years ago we started seeing a job being replaced by machines and started discussing about what AI can do, can't do, will do, I thought, there's this one job that AI will never be able to do. It's the job of doing mathematics, the job of mathematicians. And today I'm going to try to convince you that I was actually entirely wrong. So I'll start by saying that, I'll start by saying that we are all using AI tools, and we've been using AI tools for years. The most easy examples are those ones, either through social networks, emails, apps, platforms. Actually, even if you only have a smartphone, like a relatively modern smartphone, and you're taking pictures, you might be using AI tools, maybe without even knowing it. And for the general public, this thinking, the fact that we're using AI and been using AI for a long time, wasn't really something that people knew until last year. Well, last year we started hearing a lot about the progress of AI, particularly in AI for language. And this comes with a name that we've heard so many times that it's already old school. That's ChatGPT, obviously, and all of the competitors. So how did we get there? Well, the first thing to realize is that AI for language is not something new. Research on AI for language started around 1950, and the goal at the time was to be able to translate from one language to another, like German to French, German to English, French to English. And to be fair, it wasn't really working well. It's been not very working well for decades. I don't know if you tried Google Translate in 2006, for instance, it was completely rubbish. The turning point arrived in the years 2010s with the neural networks, and this led to large progress in translation. And another turning point that we're going to discuss a little bit right now happened in 2017. It's what we call the transformer. So what's a transformer? A transformer is a kind of neural network. It's an architecture of neural network that has an attention mechanism that allows you to focus on the right pieces of a sentence. For instance, in this sentence, very roughly speaking, you might want to have something that knows that there is probably a link between thin, hope, and best. That was 2017, and so this paper was released in 2017. The original paper is named "Answer is all you need," and I don't know if you see from here, but this paper, since 2017, was cited more than 90,000 times. So I don't know for you, but at least from my perspective, even if there are more citations in AI than in mathematics, for instance, I still believe this is kind of a small revolution. Now, in 2018, arrived the first GPT model, which was an implementation, an autoregressive implementation of this transformer. I'm going to say what autoregressive means right now. And this was GPT-1. So you might have heard about GPT-3, GPT-4, but this was GPT-1 in 2018, created by a company that's called OpenAI, and that at the time no one knew except people doing AI. So the way it works is the following. Assume that you have a neural network, and the goal of the neural network is it has been trained to complete sentences. So you will give a request, your query will be hope is a good. Then it will detect this sentence. From this, because it has been trained, it will compute a density of probability of the next word, and then it will sample, according to this density of probability, the next word, and here I think thing has a decent probability of appearing. And the autoregressive part is to take this and put it back in the sentence and do the same step again. So hope is the good thing. Then you look at the density of probability of the next word, and there are many possibilities for this, but because this sentence is, so hope is a good thing, maybe the best of things, and no good thing ever dies. So this is a quote from the Shawshank Redemption, so it's many places on the web, which means that if your model was trained on the internet, it's likely that you will have a comma after. And then and so on until you get the sentence. And then something saying, okay, the next word is actually a point, and then it's the end of your sentence. So this is the answer that you will get. So this is the end of my 2-minute crash course on GPT models and transformers that will be useful for later. I'm going to go back to mathematics, and the lectures of today will be in 2 parts. The first part will be what AI can do today in mathematics. What can we expect, and how can we use today as mathematicians AI tools? The second will be a bit for a longer term. We would like to know whether an AI can prove a theorem. And I mean, prove a theorem and prove a theorem by itself. So you give a statement to an AI and it gives you the proof, right? So let's not be afraid of science fiction. It might actually not be fiction, it might just be science. And my approach in all this talk is not to try to explain AI with mathematics or to help AI methods with mathematics. It's exactly the other way around. I'm trying to use AI methods to prove theorems, so to help mathematicians. So let's start with the first part, AI today in mathematics. And I'll start by saying that solving math problems with a computer is not something new. It's as surprising as it may seem, it's something that we have been doing for years now. And one of my favorite examples is this one. It's a conjecture by Euler from 1769. So obviously they didn't have a computer at the time. Euler's conjecture is the following. If you have k integers and you put them to the power n and you sum them, if it's equal to another integer to the power n, then k is larger than n. Right. Relatively simple to understand. And so Euler wasn't able to prove this at the time. And as a matter of fact, no mathematician was able to prove or disprove this for around 200 years. So this was until Mendel and Parkin arrived in 1966, and they solved this problem in the most silly way you can imagine. They just tried many different combinations with a computer, and what they got was this. So you see here on the left-hand side, you have 1, 2, 3, 4 integer to the power 5. And so if you follow Euler's conjecture, it will mean that 4 is larger than 5. And as we know, it's not the case. So this was a counterexample. So this was a new mathematical result, but most importantly, it's the only paper I know of that can fit entirely on the slide. So, okay, that was a new mathematical result, but that was mostly the proof that even when you're a genius like Euler, you can still make mistakes. The only problem is that mankind takes 200 years to spot them. In the more recent examples, there's a proof of the Keller's conjecture, the last case that was missing of the Keller conjecture in 2019. So I'm not going to explain what the Keller conjecture is. The only thing I'm going to say is that this is a proof where you can show that you can reduce it to checking many simple cases. There's already some work to do this, but you can reduce it to proving many simple cases. Each case is easy to check, but there are a lot of cases, like very many cases, like far too many for human. And so what this team of researchers did was they've been able to use a computer to check the cases, and so they finished the proof. So you might wonder, okay, many cases, but like how many? It's a finite number, so how long is the proof? But in fact, in this case, you're not even asking how many pages is the proof, you're asking how many gigabytes is the proof, and the answer is 200 gigabytes, so around 10 times Wikipedia. So if I were to read you the proof out loud, starting now, we will be until the MoD lecture of 2025. So yeah, that will be a long time. All right, so this was just to say that computers have been used to prove theorems for a long time, even in pure mathematics. But in each of these cases, the difficulty is combinatorial. You have a lot of cases. Each of the cases are relatively easy, but then there are too many for human. We can't compute as fast as the computer, so that's why we're using it. With AI, can we do more? Can we solve more complicated problems? Can we solve problems where the difficulty is just not combinatory? So I'm going to try to convince you that the answer is yes, with 3 examples coming from different areas of mathematics. So the first one from stability of dynamical systems, the second one from control theory, and the last one from topology. So let's start with the first one. So we start with a system of differential equations like this, x prime is equal to f of x. Well, this can obviously model a lot of things, like quantum free fall, the evolution of chemical reaction, solenoid economics. Well, you're all mathematicians, so I don't need to convince you that studying this is very useful. The question is this true? Is this system satisfy this property? Is it true that for any epsilon, I can find a delta such that if the initial condition satisfies is smaller than delta in norm, then the solution exists for any time, and the solution is always lower than epsilon. So essentially, are those solutions bounded if the initial condition is sufficiently small? And written differently, if I try to draw it, is for any red ball, can I find a blue ball such that if I start in the blue ball, well, I don't know what the solution is going to do, but at least I know it's going to stay inside the red ball. So that's the property I'm interested with. Thank you for being there. It starts to be a very crowded room. Very happy, very flattered. All right. So this is the properties that we're interested with. We'd like to know whether we'd like to know if all solutions are bounded if the initial condition is sufficiently small. This is the problem we're trying to solve on a system of differential equations. Now, this is a complicated problem that has interested mathematicians for over 100 years. You can cite among the very old and famous works, the works of Amaury, Poincaré, for instance, or the three bodies problem. There was one big breakthrough in this area at the turn of the 20th century that was made by Lyapunov and the consequent works. So essentially what it tells you is that if there exists a Lyapunov function to a system, so Lyapunov function is this kind of function, a function that is strictly minimum in zero, goes to infinity at infinity. And when you take the gradient of this function and compute the scalar product with the dynamic of the system, then it's lower or equal to zero. If there is this Lyapunov function, then your system is stable. So this answers our problem. So this is a very powerful result because it reduces an extremely complicated problem as finding the stability of the system to finding the existence of such function. So it's very powerful up to a small, tiny detail, which is that nothing tells you how to find this kind of Lyapunov function. And in fact, this tiny detail is not so tiny. It's actually not a simple problem. For instance, if I give you this system, so this system is actually a simple system, so you might not believe me, but there is a simple Lyapunov function. And even though it's supposed to be a simple system, it's not very easy to see that the Lyapunov function is this one. I mean, at least one Lyapunov function is this one, right? But there's no cross term in the Lyapunov function, so trust me, it's not that hard. I actually gave many systems like this to my students last week to see what was the human accuracy on this kind of problem, and this was a part of the one that the students could do.
Is this a gradient system or not?
No, there's not a gradient system. No, it's easy, but not that easy.
Yeah.
All right, so it's actually such a hard problem that I mean, you can make a very nice math paper about a kind of system that has or don't have a Lyapunov function, and this is a paper that I like from Miroslav Kristich, among others. Miroslav Kristich, I think, was the first speaker in the MoD lectures a year and a half ago. So today, more than 100 years later, there is still an open question. There is no systematic way to construct the Lyapunov function. I mean, maybe there is no systematic way to construct the Lyapunov function, no possible systematic way. So what do we do, us mathematicians, when we have to solve this problem, but then there is no systematic method? Well, most of the time we resort to intuition, right? So intuition is an important concept in mathematics. Usually, in a number of cases, it resembles a kind of pattern matching. You know, you've seen many different, plenty of examples, previous cases, and this gives you an idea for the new cases that you've never seen before. So there's a kind of pattern matching somewhere. And then you can think of this. Usually, AI is better than humans at pattern matching when trained properly. So it could seem natural to try to train an AI, so then you probably need a mathematician to train this AI, but train AI to recognize Lyapunov functions and to have a better intuition than humans, right? So can we do this? Can we train an AI to have better intuition than us? So this is what we try to do, and we try to do it with the Lyapunov functions. And this is something we did. So once again, we want an AI that takes this in input. So you give it this system, and the AI, the black box, answers, yes, this is stable, and this is the Lyapunov function, right? You're not interested in a black box that just say yes or no because you can't check it. You're interested in something that is easy to check. Otherwise, it's interesting, but it doesn't help mathematicians. You know, we want proof, we want actual theorems. So this is what we did with Alberto Alfarano and François Charton from Beta AI. The neural network architecture we chose was a transformer. That's why I talked about it at the beginning. We got something that is like at least 1,000 times smaller than ChatGPT, so something relatively small that could fit on any computer. And the procedure is the following. The first step is to generate a lot of examples. You want examples of systems and Lyapunov functions so that you're going to be able to train your model. And this is the hardest part. I mean, getting enough examples of this when it is an open problem is not very easy. We can discuss about that later if you're interested, but this is really where the mathematician parts come in. Then we encode the examples in a language that the transformer will be able to read. And then we train the transformer in supervised learning. So we show a lot of examples, and we hope that it will learn what makes a Lyapunov function better than us. All right, so I think it's interesting to see how we encode the examples. This is just out of curiosity. If you have a mathematical expression, we will transform it as a tree. And then we will enumerate the tree in a prefix or Polish notation. So starting from the top and left, so plus power x1 to sine x2. And this is the chain of characters that the neural network is seeing. And this is the type of chain of characters that the network is going to output. And then we're going to go back and create the tree and then create the mathematical expression. So if you do this, if you train your AI like this is what we're going to get. This takes, by the way, not very long. It's, I mean, on a computer, it will take a week just on your laptop computer, but or a little more, but it's not a huge training. Like, so we have different types of data sets. I will explain a little bit later. And we train, and they are all constituted of stable systems, so they all have a Lyapunov function. The question is whether the AI finds one that is valid or not. And you see, as you see, the AI is very good most of the time. This one is a little less good. It's pretty good, and I'm going to explain in a minute. But I told you that there is no systematic way of finding a Lyapunov function. I must say that in some cases, I might have lied a little bit about that, because if you are in a special case, like for instance, polynomial systems that have a polynomial function that is written as a sum of squares, so it makes a bit of a conditions. But if you're in this regime, then there are routines and algorithms that actually exist to find Lyapunov functions. And one of the most famous is source tools. So we wanted to compare with source tools what happens. So in principle, it's supposed, the algorithm is very good in principle, but then if you get some realistic memory on the computer, so for this one we capped at I think 4 gigabytes of RAM per example per system. You see that for small systems it's fine, you get a good accuracy, but as soon as you start to have a larger system with a high degree, then it drops quite quickly. Well, the AI doesn't drop much. So why are those data sets different? Well, for these ones, the way we generated the data sets is we generate a Lyapunov function and then we create the systems from the Lyapunov function. So we start from the solution. So it will bias the distribution. On principle, you can still generate all the possible stable systems, but it will bias the distribution somewhere. So to get something that is less biased, what you can do for polynomials, you can't really do it for non-polynomials, is you generate randomly a lot of systems, so completely uniformly. Then you apply source tools or any other routines like this, and you keep only the systems where source tools is giving you some solution. So it's computationally costly because you're gonna essentially discard 98% of your data set. So you generate 200,000 examples, and then you get just a few thousand at the end. But it gives you something that is a safeguard. It's just to make sure that the AI did learn the problem and not the generator. And you see, you get 83% here, which is huge. So why do I say it's huge? Because I tried on myself to see how many examples from these data sets I could find, only 2 to 3 questions and degree 6. So, and I'm about at 25–30%. I'm getting better, but still I think I'm converging to 30%. So I tried with half of the departments of a university, essentially all the students that were taking the control course. And for master students, it tends to be about 10%. So you see the AI is far above what mathematicians can do today. And the good thing is that it can also do non-polynomial systems. That's the reason why we were trying to do this. I mean, we weren't really interested in solving something that other routines are already able to solve. All right, so this is it for this example. I'm going to move on to the next example now, an example from control theory. And now we're going to deep dive in the applied mathematics. And we're going to take a system that models the evolution of a mosquito population. So you have eggs, you have male, female, a fertilized female, and sterile males. And your goal is, so you have a control. This is the flow of sterile males, sterile mosquitoes that you put in the system. And your goal is to put enough of them so that they will be chosen from time to time by the female. And this will, because they can't reproduce, this will decrease the entire population. So you see, it's a very weak control, but you hope that this will make you have less mosquitoes. Because this is a problem coming from a real life problem, you have some constraints, physical constraints, and one of them is that this control, so it has to be bounded, but also this control can only depend on 2 variables. the total number of male and the total number of females, because this is essentially what we can measure. It's relatively hard to distinguish between those two. And the question is, can I find such a control? So can I find such function f such that the system is stable, the population of mosquitoes goes to 0, and well, the number of sterile male doesn't go to 0, but goes to epsilon, where epsilon can be as small as desired. This is really a mathematical question, because when you have a 1 mosquito, it's usually fine, or 0.3 mosquito, well. So can you do this?
May I have a question?
Yes.
So that means you are always talking about averages, yeah? Since you are deterministic, this is a completely deterministic.
It's a completely deterministic system.
So
yes.
basically, you're talking about averages.
Well, there isn't even any stochasticity. So.
But of course, in
oh yeah, in real life there is. This is a
so you're
deterministic.
talking about the expectations.
Yes, exactly. So we could try with stochastic control, but well, we didn't really know if it was going to work already for deterministic. So
it was just a question.
No, yeah, that's a very good question. Yes.
For the students listening, it would be great if you could add 2 sentences on the stability.
Oh yes.
To explain it.
All right. So okay, let's put it. So I'm going to go very quickly back again on the stability. So stability, from a math point of view, is saying is like this. So for any epsilon, I can find delta such that if the initial condition is small enough, then all the solutions are bounded by epsilon. But essentially what it means that if you start small enough, you can make sure that the solution exists and will never go above some bound. So essentially you remain bounded. So you don't want to know that all the solutions will remain bounded. The only thing you want to know is that if you start small enough, everything will remain bounded. Sometimes we want to do more than that. We want to ensure what we call asymptotic stability, which means that we would like not only the solution to be bounded, but to actually go to 0, right? And for mosquitoes, I mean, you can understand we want no more mosquitoes. So we want the population to go to 0. In this case, we want the population of mosquitoes to go to 0, but it's not completely an asymptotic stability from the sterile male perspective, which is the control variable, because we allow an epsilon here. But epsilon can be as small as we want. So this is really the goal, bringing solutions to 0. This is a large field of research, and this is an open question for this system. I mean, the goal is to make this you want it to go to 0 for this time any initial condition. So it's pretty hard. It's hard because the system is very bad actually. The system is non-Lipschitz, close to 0. It's not very continuous. Then here you have some constraints. I mean, the constraint on the control is very hard to ask for this type of variable. So I wasn't able to do it. Some top mathematicians were unable to do this as well. So we thought, okay, maybe we can ask an AI and ask the AI to give us an intuition and hopefully a form of the control. So this is what we tried with FAU Jean-Michel Coron and Nathan Vichelet in 2023. And the approach that we introduced for this is the following. You have a system of equations. You discretize them with a well-chosen numerical scheme. So you have to be very careful here. This is, everything is hidden in the well-chosen, but for finite dimensional systems, essentially it's fine. Then you train a reinforcement learning model. So an AI that trains by trial and error and tries to maximize a well-chosen objective. And I think we chose a standard one, but there are probably many better options, and I think the group of Enrique Zuazo is developing things that are probably better than what we were using. Then we have if it works, if the AI converges to something, then it converges to a numerical control. So you have a black box to which you give some numbers, and it will output numbers. And you want a mathematical function. So there starts the job of a mathematician to try to analyze this black box to understand what is behind. Can I find a formula that looks like it's behind? And what's important in this formula? What makes it work? And then you can check that this is a solution to the problem. So a mix between AI and mathematical analysis. So we did this for the mosquitoes problem, and it worked. I mean, the AI converged to some control, to some numerical control. So I told you that the control depends on 2 variables, M plus MS, the total number of male and total number of female. So here on the scale is the total number of male, and here's the total number of female, and this is the numerical control. The color is the value, essentially. So when it's very dark here, it's 0, and when it's yellow, it's a maximum value. We are bounded. We can't give more than 500,000 mosquitoes every day. And well, the numbers were given to us by people actually doing this. I didn't discuss it. So, and I don't know for you, but when I look at this this map, well, I mean, I have to find a mathematical formula, and you know, that's I don't really see something coming in here.
So the algorithm doesn't give you an analytical
No.
expression?
No, the algorithm gives you some
The graphs.
yeah, the graph. So then it's up to you to interpret. So we are
They are
trying
bang? No, I mean, there is contrast, right?
exactly,
So
exactly. Right now there is a transition. So it's not exactly bang bang, but we'll see in a minute that we'll end up with something that is bang bang. We are also trying right now to work on something where the algorithm gives you this, and then you have another AI that is trained from this to give you an analytic formula. Actually, we wanted to develop this for this work, but we didn't need it to. Thanks to one of my PhD students called Nathan Lichelet. So essentially, so I don't see anything when I see this, but when he sees this, he sees directly that you have to put it in log scale, and it gives this. And now it's much easier to see what's happening. Essentially, you've got max value, lower value, and then you have a transition that is more or less smooth here. So you can find a formula for this. It's maybe complicated, but there starts the job of the mathematician. What is important in this formula? What makes it work? And it appears that the part that makes it work is just this one. So something that is essentially bang bang but the frontier is what depends on the measures. So, and to be fair, looking at this, I would never have guessed a control like this. I mean, I don't know for you, maybe you have better intuition than me. I don't, so I have to ask the AI for intuition, but yeah. And when you do this, it seems to work. You have, it does converge quickly to the equilibrium you're looking at. What's interesting is that this works for any epsilon positive, but if you try to take epsilon equal to 0, it doesn't work anymore. So with something that is as approximative as a neural network, you can still see some subtle phenomena such as a mathematical bifurcation. So this is something I really liked about this example. All right, so I'm going to now give my third example and see the time is running, so I won't spend too much time on this. This is taken from an article that was published in Nature in 2021 by a team of DeepMind and the group of Jordi Williamson in Sydney. The principle is the following. You have some mathematical objects Z. Well, they have quantities, x of z and y of z. Let's call them this very high level right now. And you'd like to know if there is a link between x of z and y of z. So what can you do? Well, you can try to train a neural network to predict y of z from x of z. And if the neural network converges to something and manages to have accurate prediction, it means that there is a link. You don't know the link, but it means that there is a link. And then once you have your neural network, then you can try to do exactly as we did with our numerical control. You can try to attack the neural network to understand what's behind, and maybe understand the link. So on a concrete example, they did this to get a link between hyperbolic and algebraic invariance of nodes. So I don't remember whether this is only a conjecture or has already been shown. I think it might have already been proved since then. All right, so this is the end for this example. And I hope I managed to convince you that AI is already useful in the practice of mathematics and has helped to solve several difficult problems. Now, in all these cases, AI is trained to have a better intuition than humans on specific problems. And this works particularly well on problems that are really hard to solve, but showing that a candidate solution is a solution is relatively easy. So something where if I give you a kind of joker, your candidate solution, then it's easy, you're probably going to make it. And so this augmented intuition, in fact, is used to cheat a little bit, to bypass the difficulty of the problem by getting directly a candidate solution. All right, so this is it for this part. Now there's a question that you might ask. Okay, the AI is able to do this, that's great, but can we go even further? And can an AI prove a mathematical result on its own? I mean, can an AI reason, or there are some philosophical questions behind. I'll essentially look at the first one, not really the second one, but it's linked. And so this is the goal of this second part. So the main question is, can an AI find a proof for a mathematical statement? So you write to the AI, please show this, and the AI outputs a proof for this. There's a related question. So this has been investigated by many research groups around the world, in these places, but not here, of course. As you see, there are universities, but also some private companies. And there's a related question. Can we automate, at least partially, human reasoning? Is there a way we can have an approximation of the way human reason that will be automated? It doesn't have to be AI. It will be good old-fashioned AI, as people call it. So it's a non-neural network. And there's a research group led by Timothy Gowers in Cambridge about this. So if I ask you, okay, if I ask you to train an AI to prove theorems, what is the first thing you might think of? Okay, what do you want to try? Yes, anyone?
Set theory.
Set theory, okay, but what kind of AI would you try? Well, you might try to train your own ChatGPT to do math. Right? That's the first thing to do. And this was actually done in 2020. So this was done in 2020 by, so right after GPT-3 appeared, but before ChatGPT, of course. This was done by Stanislas Pollu and Ilya Sutskever. So I don't know if you followed the OpenAI drama last November, where the CEO of OpenAI, Sam Altman, got fired and then reinstalled a few days later. But Ilya Sutskever was at the center of this drama. He's the chief scientist of OpenAI. He was might have been the mind behind this failed coup. But in fact, apart from being one of the main actors of this failed coup, Ilya Sutskever is also one of the most impressive and prolific researcher in AI of the decade. You see here, so this looks like a Google Scholar profile of a young researcher, but the little point here, 2014, is 2,000 citation. So the guy has been cited 400,000 times. His age index is 84. He's not even 40. So this is what the chief scientist of OpenAI looks like. Okay, that's the end of my parenthesis. Just to say that these guys made the GPTF, and GPTF works as follows. You give it a question, you have your GPT model, and it gives a proof. And of course, you all know now how a GPT model works, so we're going to look at it. You have a math statement. You're going to compute the density probability, not of the next word, but the next step. So you sample the next step. You put the next step here. You compute density probability and so on. And at the end, you hope that the AI is good enough so that when you have enough steps, it says, okay, density probability is here, then I sample, most likely this is the end of the proof. This would be the ideal, and then you take the right column, and this is the proof to your mathematical statements. Now, this is a bit of a naive way, because you can actually do better than that. If you have your statement, and if everything is written in a formal language with a computer assistant, and you can, in live, see what happens when you apply step 1 to the statement. What you can do is the following. You can have a statement, compute density or probability, predict the first step, sample to get the first step, and then you apply the first step, so you'll get a new statement. Right? And then you do the same again. And at the end of the day, your computer assistant will tell you there's nothing left to prove. And then you don't need even a neural network. You just need, nothing left to prove and a proof. Right. So this is the hope. And when you're doing this, you're going to train your GPT with lots of examples, exercise, proofs that you're finding somewhere. And the hope is that by showing it enough examples, the AI will be able to reason in some sense, to prove theorems just by learning to predict the next step each time. So you might be skeptical, either because you believe that an AI will never be able to reason, okay, that's one thing, or because you believe that just looking at the next step, it means that you have no long-term view on your proof, and so it might be too limiting. But on the other hand, if you think of ChatGPT or GPT-4, all those models only predict the next word. And they still manage to write beautiful essays. So, yeah, it's surprising, but it works. So I don't know, you might be skeptical, you might be optimistic, but whether you're skeptical or optimistic, in any cases, this can only work if you have enough examples. And enough mean sufficiently diverse and sufficiently numerous. And this is the main problem, because we don't have that many examples, especially formal examples. So what do I call formal? Well, you have two types of language, two types of data that you can get. Informal data, so that's exercises that are written either in English, in German, in French, something that will need to be corrected by a human reviewer. And formal data, something that is written in the language of a computer assistant that can automatically check the proof. So this can be checked by a computer. There's no way to cheat. There's no mistake possible in here. Now, the problem of the first one, what's nice about the first one is that it's what we're doing, but the problem about the first one is that it might be much easier for a neural network to learn how to cheat and to fool a reviewer rather than proving actually a theorem. And even with formal data, it took us some time to have the neural network stop trying to exploit the problems in our kernel to make it work. In formal language, if you have a good formal language, you have a 100% guarantee that things are correct, so the neural network cannot cheat. Either it proves the theorem or it doesn't. So that's why many people like to use formal language. The problem is that we don't have that many data of formal language. We have 100,000 theorems in Lean, so of course for a human this seems huge. I mean, I'm very far from being able to remember maybe 1% of these theorems, but from an AI point of view, it's relatively small data sets. For this kind of language model, you will hope for at least 1 million examples. So if you want to know, so this is the limit of the approach, which still works to prove this kind of exercise. I mean, it still works up to some, it has some limits, but it still works a little bit. And if you want to know what's possible and not possible, or what are the limits of what you can do with this, you can look at this paper from Fabian Glöckler of 2023, temperature scale large language models for Lean proof step prediction. It explains it well. Yeah, I'll just say that Fabian is a very impressive first-year PhD student, because it's essentially his third paper, I think, and he started less than a year ago. So, all right. So this is it for this first approach. The second approach is about treating mathematics as a game. Right? We all know it's a fun game, right? Otherwise, we wouldn't be here. And the motivation is the following: DeepMind in 2017 released an AI that was able to learn chess against itself. So you give it the role of chess or of Go, nothing else, and after 3 days of playing against itself, it becomes better than any human on Earth. So we thought, okay, let's do the same with math. You know, math is we're gonna turn math into a game, then ask an AI to train against itself, and after 3-4 days, it's gonna be better than any mathematicians on Earth. What kind of game is this? Well, this kind of game, you get a statement, you make a move, so it means you apply a theorem. When you apply a theorem, you have assumptions to satisfy, so now you have to show the assumptions. So you make another move, then this theorem has no assumptions, so that's fine. You have nothing left to prove, and then you make a move, you make a move, you make a move. And if at the end of the day you have nothing to prove, you won. That's the goal of the game, right? Again, a very fun game. So the problem is that there are many difficulties compared to chess and Go. The first one is really an AI difficulty. Training an AI for a 2-player game is much easier than training an AI for a solo game. Why? Because on a 2-player game, imagine you are training an AI to play chess. Well, you start with AIs that are very bad at chess, but you make them compete once against the other, and at some point when you have 2 of them competing, well, one is likely to win. So even if they're very bad, one is going to win, and you know that this is a better way of playing than the other one. So it gives you some feedback, and then you can keep training, and you hope that this will keep going like this, and the AI is going to be very, very good at chess, and this is what happens. In math, now you have a lot of AIs. They are all very bad at math. They're trying to prove something. None of the AI managed to, and that's it. So yeah, that's a problem. The second problem is that when you're in chess, when you play a move in chess, so just to summarize this, essentially, in chess, you don't need to be perfect to win. You just need to be better than the other one. In math, if you're almost correct, it means you're false. So then that's the hard part. In chess, when you play a move, you always have a single game. You know, I move the bishop, I only have one chessboard. In mathematics, I apply a move, that means I apply a theorem, and I have to satisfy the assumptions, so I might have 2 statements or 3 statements. And this is not a problem per se, but if I do this a lot of times, I might get an exponential number of statements to show. A human will never do this, but a machine that's training maybe. And this is going to be a problem. Of course, in mathematics, it's in chess, we have some approximations to know who is winning. You know, you can that. The crudest approximation, just counting the number of points, but you know, we have approximations to say, okay, this person is likely to win. In math, it's quite hard in the middle of a proof to say, unless you've already done all the critical steps, it's quite hard to say, okay, I'm this likely to succeed. It's even harder to make it, to have a computer saying it. And the last problem, that's an obvious problem, is that the number of possibilities is much, much larger in mathematics than in chess. I mean, in chess, you have what, 100, 2,000, 100, 200 possible moves? In mathematics, you have so many things that you could try. I mean, you can say, you can introduce a new assumption, you really can do many, many things. So this is just to prepare you to the fact that we haven't trained an AI that is better than any mathematician on Earth. Yeah, fortunately. All right, so what we did is the following. We used, we've been seeing the proofs for a statement as a huge graph. All the possible proofs is a huge graph. And if you manage to find a subtree where you have nothing to prove at the end, so no leaves, it means that you found a valid proof for your statement. This is what we're trying to find. And to find this, we couple two things. Two transformers, so two AI. The first one is like the previous one, like the GPT one. It predicts the next the next step of the proof. But instead of sampling, so it computes the density of probability, but instead of sampling one, it can sample many of them. So you sample many of them, you apply them to see what it will give and what are the assumptions that now you would like to show. And then you have the second AI that is trained to say, okay, this is going to be hard to show, this is going to be easy to show, this is going to be impossible to show. So that if you go back to the say the steps A, B, C, that's the possible steps that you sampled, you can say, okay, no, this one gives rise to assumptions that are impossible to show, I discard it. This one I keep it, and so on. So we couple this and an efficient proof search, so that when you're exploring the graph, at the same time, you will keep training your two AIs. And this is essentially what we did to have this kind of neural network, and so an ensemble of neural networks that will be trained to prove math statements. And what it gives at the end is this. It's a neural network that we call Evarist. I didn't choose the name. That is able to show exercise at undergraduate level. And so 30 to 60% exercise of middle school, high school exercise, but they were exercise essentially of Olympiad levels. So that's why they're a bit harder than, you know, there are two types of difficulty. Difficulty where an exercise where you have to be smart, and exercise where when you have to understand deeply the notions that you've seen in lectures. Understanding the notions in lectures and seeing the links with another notion is not really a problem for the AI. It can memorize so many things. Being smart is a whole other story. That's why we're training on Olympiad levels, because this is the hardest for the AI. And sometimes it did work on it did prove a few exercises from the International Mathematical Olympiads. So for instance, this one, so you want to show that for any n, 7 never divides 2 to the power n plus 1. So you can try, it's a good exercise. I think I met someone once who told me this is extremely easy, not a mathematician, so it's extremely easy. Look, okay, I start, 5 is fine, 9 is fine, everything's fine. I say, okay, yeah, and now n is equal to 2 to the power 42. And then, so obviously, it's not super hard to prove, but it still needs a bit of thinking.
So it's done by induction or not?
Yeah, it's proved by induction. So you have an induction somewhere in the middle.
And then the artificial intelligence understands
induction. Yes, completely. Yeah, the artificial intelligence actually wrote induction, the columns. So I can show you a proof if you want after. So this was done with a large team. We were 8 with Guillaume Lampe, Marianne Lachaud, Thibault Lavrier, Xavier Martinet, Gabriel Ebner, Aurélien Rodriguez, and Timothée Lacroix. Among us, like 5 were full-time researchers on it. So it was really a huge effort for 2.5 years. I say only to get an AI that is able to do this, but this is already, I hope, impressive in some sense. The thing is, we're very far from being able to have an AI that is at the math level, and it's not a question of the size of the model, of the engineering behind. It's really there is a need for more mathematical understanding and new strategies to get. So I think it's a very interesting subject. It also had some unexpected outcomes. After we did this, most of the team had to work on the Llama neural network, and quickly after, Guillaume Lampe and Timothée Lacroix resigned from Meta AI, because they were from Meta AI, and they founded a startup called Mistral AI that is making large language models. 1 month after they launched this startup, they raised $100 million. And last month, so 6 months after, they raised $400 million. So now they have a $2 billion company. So I don't know what to deduce from this. Maybe we can deduce that it's harder to have an AI that proves math than to launch a 2 billion startup. Well, that's just a parenthesis, because I'm very impressed by these guys. Okay, so this is the end of my talk. I think there are many perspectives here. The things that we would like to add, I think there are missing things. we would like to add approximations of human reasoning, because this sampling proof steps and looking at the hypothesis and what's going to be hard to prove, it's nice, but it's really a very crude approximation of human reasoning. We'd like to have better heuristics. You can want to have a neural network that has a hierarchy between the proof steps it shows. You know, not all proof steps are equally important. You know, replacing 2 + 2 by 4 is probably not a key step of your proof. Applying dominant convergence, for instance, might be a key step for your exercise. So you would like the AI to know that there's a hierarchy between the different steps. And of course, we would like to have more formal data. And there are many people working on this, trying essentially to get an exercise that is written in English or in German and in French, and having an AI that goes from this to a correct proof in a formal language. In particular, if this was extremely good, but we're far from this, you will be able to, I don't know, put an article that is on archive in this, and it will check the validity of the proof for you. And that's a dream. I don't know if you'll have it one day. So I hope that during this talk, I convinced you that AI is useful in the practice of mathematics. I think AI for proving theorems is only the beginning, but there are still many ideas and much to do. So I think this is a promising area. We'll see. I think that the practice of mathematics will probably change in the next decade, but that's fine. It has always been changing anyway. And I think definitely that AI will not replace mathematicians, but instead will really enhance them. And this is the end of my talk. Thank you very much for your attention.
Thank you, very inspiring and fantastic talk. Thank you, Amaury. Okay, so we have also, I don't know, like 150 colleagues watching online. Many of them are still there. So maybe we can give them first the opportunity to raise questions, either written or spoken if possible. Yeah. Any? So these are questions that are written, or
no, these are all comments.
Okay.
There's no questions yet.
So questions for people that are remote.
Eugene, please go ahead and unmute yourself.
Yeah, thanks for the excellent talk, and forgive my ignorance. This area is very far from my research expertise, but one thing that you mentioned was that one of the difficulties is for training AI is the lack of examples. And at the sort of penultimate page, we had the last bullet point saying the self-formalization effort, etc. So my question is about the following. There is a great deal of research on sort of formalizing mathematical proofs, basically not formalizing formal proof verification, to be more precise. And for example, there is a number theorist, Kevin Buzzard at Imperial College London, who does a great deal of research in this formal verification of proofs. So my question is, could one just kind of borrow whatever they do and then train AI on those? So because they do a lot of stuff there, they formalize proof, there is a lot of, I think, there might be a lot of things that can be used for training AI. Maybe this is already done, and maybe what I'm saying is completely bonkers. I don't know. I'm very...
That's a very good question and a very good remark. So actually, yes, Kevin Buzzard is actually a great researcher. I mean, I've been very impressed by his work. And this is actually what we already do. I mean, when I say that there is 100,000 theorems in Lean, we haven't made them ourselves. It's actually the work of Kevin Buzzard and the people working this area. So we are. You're nice to say that we are borrowing it. Yeah, I was about to say we're just stealing what they put online, but no, that's yeah. We've been discussing with them a lot to know what we could do, because the very first step, even if this is not perfect, one thing that it could do is show some small steps of proof. So if you're not, so of course for the people who are very good at in this area of research, they don't need us to write formal proofs. But for people who are beginning, they might say, okay, I want to prove this, and then the AI can suggest many steps. So at the beginning, we wanted to do something like this, to have some interconnections. But right now, I think we are more using their work than they can use ours. I hope this will change in the future. But yes.
Thank you.
What is very nice also, it's a very dynamic and very responsive area. I mean, I remember on the Zulip forum of Lean, where the speaker are, I think I've asked many questions. I've never waited more than 15 minutes to get an answer, which really amazed me.
There's another comment in the chat that says, so we conclude that to train AI, we have to work more than AI to make it a mathematician.
Yeah, well, kind of. You can hope that one day when you have enough examples, then the AI will make you go faster, and then it will be worth it. At the very beginning, it's like for big computations when you're doing offline computations. The first one is always much sharper. Yeah. No, I think it's there will be a large need of mathematicians, which wasn't completely obvious from the beginning, because for large language models, for language, at the end of the day, linguists didn't have really their word to say about the machine's really learning by itself. And some people in AI were hoping that this would be the same for math. It happens that it doesn't seem to be the case.
Nicola?
Okay, thank you. Actually, I have naive questions because I'm not an expert in the field. So first of all, I highly appreciated your talk, and I've learned a lot on this interesting field. Just a curiosity, in the technical learning process which appeared in your examples, there is always a quite strong rationality presence. And for instance, in the game interactions, the players have a payoff, an objective which is somehow defined. My curiosity is the following. What about substituting the payoff with what has been called by Herbert Simon a utility function, where the utility functions evolves in time due also to the action of the players?
That's a very good question. If I go back to the...
So thank you, Nicola. Nicola Velomo, right?
Yes, exactly. Yes.
Okay,
still the same.
Yeah. Thank you, Nicola. Hello.
Yeah, it's most likely, sorry. It's relatively close to the end. Yeah. So here, actually, we struggle to make it work, even with like a player's game with a rational payoff, because if we just if you just give a payoff, we have a payoff at the very end if it works, but it's essentially 1 or 0. So and this doesn't give you any. I mean, you try to prove something, you do many steps, and at the end of the day, you get 0. You didn't manage to prove it, and the feedback of 0 will not help you much to know what you did wrong. So it's already relatively hard even to do like this. So I think the utility function question is a very good question. I mean, it's you will have to. I think it's close to what we actually do here, because here we have a function that is an estimation of whether what we did was interesting or not, and whether we are going to be able to prove the theorem. And this kind of payoff function varies within the steps. So the more you get into the graph, the more it will change depending on your action. So it will indeed look a bit like, so it's not with time, it's with the number of steps you take, but it will change with your actions. Now, maybe we could improve the way it's changing with the actions, because right now it's essentially a trade-off between this model, the one that we trained to say whether something is hard or not to show, and what we've already seen in the graph. So there's a payoff, there's a trade-off, and of course, the more you take actions, the more it increases the weight on what you've already seen. So the learned knowledge is supposed to be better that way. So I think it's really a very interesting question. I'm not 100% sure how I would implement it like this, but you see, I think this is typically the kind of idea that we need to try to get something better. So yeah, we'll also see what the other people do. Apparently, following the OpenAI drama, some of us heard about the Q-star algorithm that they have, or they're supposed to have, it's supposed to be great. Well, if I understood correctly, it's kind of a proof search, so we'll see what kind of proof search they're using.
So this is maybe like correcting exams, right? Where the answer of the students is not fully wrong, is not fully correct, and you have to grade from 0 to 1 and say, well.
yeah, you'd like to give us each time you're taking
It's
a
not
step.
simply to say it's wrong, because it's not a zero. I mean, you might be almost,
Yeah, exactly. Each step you're taking, you would like something that is able to tell you either one, if this is the perfect step, zero, if it gives something that's just not going to work. But the real difficulty is, this is likely to be a good step or grading the step in the middle.
I remember very interesting discussions, right, with the students. I mean, asking, we asked about the integral of a positive function, and the result was negative, right? But still, there was some tough negotiation about how many points, right? So because I was using the fundamental calculus, which is true, right? So
yeah, that's
so,
typically the type of thing.
This is human intelligence. Yeah. Okay.
And human intelligence is not that bad at learning itself the feedback. So essentially, we don't have something that corrects really. The error you really need to grade it to find details. Ideal. You would like to find an automatic way of doing it. And this is the hard part.
Interesting. So, but somehow the question by Nicola was related to reinforcement.
No, it's okay. I think that this kind of thing, this kind of thing should be discussed in the future, because it's an interesting way to go on. But I am very happy of the reply. Thank you.
And we have another question online by Sylvia. If you want to.
Yes. So my question is nothing to do with your talk, because I'm not a specialist. But I am wondering, you are talking about an AI which is able to find a proof of a theorem.
Yes.
And my question is, do you think that one day an AA would be able to find a mathematical theorem?
Okay, I'll start by saying I think so. But I think we're still, I have many colleagues asking me, so I have one colleague who told me he would register for unemployment. So I think so, but I think the first step that will be AI with humans, so essentially humans enhanced by AI that will ask, you'll ask some intuition about the next step, or what is the AI proposing you. And I don't think that AI alone will be better than human plus AI. But I think that we could have an AI in the future that will be able to prove a theorem that we're not able to prove. Maybe not the Riemann hypothesis right away, but I think something research level is definitely possible. I still think that we are light years from being able to do this. So maybe we'll go faster than light in the next few years. I don't know, but at least right now, we still are light years from being able to do this.
Okay.
But transformers, there are generative also.
Yeah, transformers are.
So cannot use generative transformers to say out of in I build another theorem?
Yeah. So we try to train, actually people try to train transformers to say, okay, this is a new theorem that is correct in math for some time. When I arrived in this field, that was early 2020, trying to do this. The state of the art was a paper, I don't remember by which company, so I don't want to say anything, so I don't want to embarrass anything. But I think the state of the art was we have something that generates new theorem. Here is a new theorem, x is real, so sine of 3x is real. So I was like, okay, that's indeed not in the database. And so then we started, we created actually a generator of, to have more data, we created a generator of exercise. With Guillaume, mostly with Guillaume Saint-Simon de la Croix, but with essentially the entire Évariste team, to get a lot of new theorems in some sense, but they are essentially exercise with equalities and inequalities. They would be like high school exercise, pretty tough for a high school exercise, but well, now you can choose the difficulty. And it took us a very long time to be able to have something that actually outputs something. So outputting something new is easy. Outputting something new is useful is hard. And defining something useful a priori, so is hard, because of course you can say this theorem is useful. It has been used by many people. But when you just generate the theorem, knowing whether it's going to be useful or not, we try many heuristics. Like I don't know, you have an inequality. You want the inequality you get at the end to be significantly different from the first one. So then the neural network says, I got the perfect solution, just exchange the standard inequality. So that, you can say I want to mix that. You can say many things. At the end of the day, you often get something that is very bad. At the very end of this project, we started to have an AI that was able to kind of generate something and say it's bad if it's too easily proved. So I think that will be a good approximation. And it generated exercise where, honestly, I have to think 2 minutes before, 2-3 minutes before being able to solve it. I mean, there was some non-intuitive Cauchy-Schwarz behind. So yes, but being able to, I think one of the main difficulties, that's a very related problem, because if you are able to generate good theorems, then you have unlimited amount of data to train your AI, so you're good. You can train once against the other. The real problem is what's a useful theorem? Yeah. How do you define that, and how do you give this kind of payoff to your AI if you use some kind of personal training?
There's another question in the chat, which says, why neural network type AI? What about other AI and optimization methods? Is there any proof that neural networks based AI like ChatGPT is better in maths than anything else?
No, there's no proof that AIs like GPT are better than anything else. So the real and honest answer to this question is the following. This project started because when I was a PhD student, I was interested in AI. Not necessarily, I mean, I have no merit in this. It's just I had friends that were doing AIs, and so I was following what they were doing during their PhD, and same. And once during lunch, we discussed with a friend, say, okay, one day we'll do AI for mathematics. And because the AI for language was very advanced, and then people I was working with were very good in the AI for language, we started doing this. I feel like in the AI community, so computer science, I feel like many people are doing this kind of AI for so deep learning, NLP-based model for mathematics. I don't know whether other models will work better. It might be that a lot of people are doing this just because these kind of models are trendy. But that's a very good question. That's my honest answer.
So maybe it's time to let people in the room ask. I'm sure you have many questions also in mind.
I do have one which is quite basic. So you're asking computers to output proofs.
Yeah.
But if I go back, for example, to your case of the Lyapunov functions, then your computer is not really outputting a proof, it's outputting a candidate.
Yeah.
Now, checking that candidate Lyapunov function is indeed a Lyapunov function may not be that easy.
Right.
So but in contrast, the SOS tools to which you were comparing actually does that for you. For a smaller class of systems, granted, but it is actually checking all of the constraints.
Yeah, it is actually checking, and so when you output the Lyapunov function, it's not checked. Well, the first thing I can say is that for this particular example, if your neural network outputs a candidate Lyapunov function, you can check with the source tools quite quickly whether it's a function, and it doesn't cost the same. Because no, sorry, I mean for polynomial.
Same cost.
Same cost. You need to search. No, but there's no search involved.
Same difference. The cost comes from the semi-definite. Never mind. We can discuss that, but the cost of searching is almost the same as the check.
Okay. Well, the thing is, indeed, it might not be easy. That's why you still need mathematicians behind. It might not be easy, but you can very easily get an idea of whether it works or not, because in many cases you can try to see. This is finite dimensional Lyapunov function, so you can just try to optimize it or minimize the numerics and see what's the max value that you expect and where. And except for tangential cases, and you realize that we only work 99% or 95% of the case, it's probably because the 5%, we are rejecting a lot of cases. Essentially, we're saying it's fine if the gradient of this scalar f is lower or equal than 0, but actually we're rejecting everything that is not strict to make sure that you have something correct. So I feel like those crucial cases, those critical cases where we are on the edge, will still be hard to check. Yes, definitely. And the AI was not going to do it for you, because by definition, you won't trust what the AI is doing. And asking the proof to the AI is much, much harder, even specialized at checking Lyapunov functions. Although it could maybe be trained for this specific task, because if you just have one task, which is, I have this kind of Lyapunov function, let's say polynomial, for instance, to simplify, and I want to check it's positive, you might have a way to generate proofs. You might have a way to generate proofs that might be ugly, but that will be just like you will do either in well, using software this time, or so you might train the AI to learn the semi-definite programming. But yeah, definitely. Well, yeah, you can.
I also have a follow-up if no one
Yeah,
else.
please.
And the follow-up is, what about trying to identify limits? So I could hope to generate or suggest Lyapunov functions for an ODE, but I suppose I want to identify or do some Lyapunov analysis for a PD. Now, one strategy would be I do truncation, and then I identify the Lyapunov function for the truncated system, and then I keep increasing the number of modes in my projection, and then hopefully I can pass to a limit. Do you reckon there's any chance that AI would be somehow?
AI could try to do this. The only problem is that if you start looking at equations, like if you start looking at nonlinear hyperbolic PDEs, for instance, well, you can increase the number of nodes as you want. This might not converge to the solution to the final PDE. So the AI is not going to do better than that. I mean, the AI is going to do exactly what you train it for. It's probably not. It can generalize to the problem you're looking at. It's not going to do something much better. So we are actually very interested in trying to do this for PDEs after. It's more complicated because then instead of searching for a function in the functional space that is already large, just like function from Rn to Rn, you might want to search for functions from, I don't know, L2 to L2, and this is yet another story. How do you write these functions? So we are really at the beginning of the reflection, so it's a very interesting question. I think here again, the main difficulty is, what are you going to give as training examples? How are the training examples be written? And yes, that's
so. For instance, you take a nonlinear elliptic PDE to determine whether it's variational or not.
For instance, yes. For instance, something like that you.
It's not far from Lyapunov.
No, this is not far from
Lyapunov. Finding the energy.
Yeah, exactly. We're trying to do this, for instance, from lax pairs. We're trying to see if we can predict lax pairs from systems. It's a bit harder because generating examples of lax pairs, unless someone has a very good idea, and I'll be happy to get it. Is, usually you know that this system has a lax pair, you know that this system has a lax pair, you know that this system has a lax pair. It's a bit more complicated to write in general. You can have several classes of systems. It's sometimes hard to make the link between the two. But this is what we're trying to do with researchers named Alexandre Krajenbrink from Cambridge, and Irene Desiraju from Sydney, and François Charton from École, who's the person doing a lot of AI for mathematics at Meta AI Paris.
So specifically for the AI for mathematics now, do you think where do you think the focus is now, in improving the data sets or improving the architecture or the prompting?
That depends on which sub-community of AI for mathematics, I would say. It depends if you include mathematicians only or mathematicians plus computer scientists interested in mathematics, or if you look at the AI community. Because if you look at the AI community, I think that the focus is clearly on proving theorems and more on the data part than on the architecture. But this is because there are a lot of people who are either computer scientists only or computer scientists with just very few mathematicians, or aiming to publish in AI and for the AI community, not necessarily for the math community. This is the big part of the community. Then the community is much smaller, and there I think people are essentially trying many different things. Even though it's not AI, the group of Timothy Gowers in Cambridge is trying to know how the human is reasoning. So you could, it's not exactly the architecture, but it's still how the implementation is going to work, or what you put on top of this. And this is, I think, a very important question, and it's probably very hard, but I'm sure they can make it, and this will be very interesting. There are other people who are investigating a lot of transformers. This is typically what François Charton is doing. Says it's more interested in what the transformer can understand than really putting methods like, can transformer understand GCTs? In which, to which extent an AI can learn the same math as we do. And so it's really clustered after, I think. So there are very different approaches. Yeah, that would be my answer.
Further questions or comments? Yes, Alice.
So yeah, thanks for the talk. It's very interesting. Brief question regarding the Lyapunov discussion. So I mean, this is a very elegant way of doing this because once you've found a Lyapunov function, you're very happy, right? So this is so you need just some. Yeah. So have you tried playing this? So the question of robustness is not that critical here. The robustness of the algorithm finding a function. But still, I'm asking. So have you tried with different initializations? Has this been kind of stable, or?
Oh yes, yes. We're so it is an important question, the question of robustness, and I think it's linked to another question that's very important. Is this out of domain generalization? Like you train on a certain domain. If you ask for something that's completely out of the domain, it's not going to work. And the funny story, so this is why we added this data set that was a little bit harder, and we added some other ones. We added some gradient flows as well. So we're not training on gradient flows, otherwise it's just going to learn gradient flows, but we're testing on gradient flows just to check that it still works on this. Otherwise, there's a... So if you look at, these data sets, this one indeed is completely out of distribution, the way we generate it. So this is where we can see so the robustness of the training with respect to the seed, and this is not really a problem. It does converge most of the time, but in any case, we're not training one model, we're training 5 at a time and seeing what happens. The robustness with respect to the distribution is very important. There are, and this is always a question when you train transformer to do something. The funny part is that we had this line, so it's a bit better now, but we had this kind of line without the source results around in 2020. So one of the very first work we tried was training the Lyapunov functions. And it was working so well that we thought, okay, the model is not learning anything, it's just learning the generators. It cannot be learning math at this rate. Let's forget about it. And we forgot about it for a year and a half. And during this year and a half, we tried the controllability. There was Prof. Chaton tried the matrices. And an AI learned, you give a matrix, and it learns, I don't know, the eigenmodes. And it was working so well all of these times, and especially out of distribution. For instance, for the controllability, we're training on systems of 5 equations. Then we were testing on a system of 6 equations. The AI has never seen a system of 6 equations before, and was working 80% of the time still. And so then we thought, oh, maybe it was actually working in 2020. And then we started working on this again, beginning of 2022. So it's a fundamental question, because what you don't want is learning the generator of examples. Because if you do this, you haven't learned anything except...
Yes, can.
Yes. In this table, I wonder why the result for non-polynomial result is better than for polynomial.
So that's a very good question. Okay, here, so I don't say completely. So the AI could be trained on many different data sets. This one was trained on the same type of dataset as this one. This one was trained on the same type of dataset as this one, and this one was trained on the same type of dataset as this one. For this one, we tried all of them, because this is out of distribution, so we tried all of them to see which one was the best. And by the way, this one, to be honest, I need to say that the AI has several chances. So we have something that checks that it's a Lyapunov function, but it can try, I don't know, like 10, 15 examples, and it has like, can check 15 different things, and if one is correct, we count it as correct. It happens that the best one on polynomials, and actually I think the best one on those 2 datasets as well, is the AI that is trained on the non-polynomial. So it's a special non-polynomial, but essentially training on this dataset seems to be better than training on anything else for all those datasets. It's surprising, but not completely surprising. In matrices as well, you want to predict the eigenvalues and the eigensystem of a matrix. There was some study there's again the article of Prof. Chaton where he sees that actually one distribution of matrices is actually training the AI in a better way than all the others. So it's a very good question, and it's likely that it's better to train the AI on this type of data set. So this one is non-polynomial. It's not completely truly non-polynomial. It's a polynomial. It's systems that are polynomial with non-polynomial operators inside the polynomial. So we have a truly non-polynomial with fractions, square roots, and so on, but we didn't have this at the time, just because if you do this, you need to keep track of the domain of validity. So from a math point of view, it's not very hard. From an engineering point of view, when you have to put it in the code, well, it took me 2 days. That was last week. So now we have other results. But indeed, that's a very good question. training, the data sets on which you're training has a lot of influence on the rest.
So then it would make sense to consider the classical classes of polynomials that are somehow dense or sufficiently orthogonal, like Hermite polynomials, or
It will make sense to try this and to see if it's better than the others. It's hard to predict which one is going to be better at the beginning, but it will make sense to say, okay, now I'm training on this type of polynomials, on this type, and see if one of them is actually better than the other. Usually, it's better if it can challenge the AI, essentially. The more it can go far away. And so we don't know exactly the internal representation of the space of function for the AI. It's an efficient space, so we'll be able to represent it. We don't know how the AI is seeing it, but it seems to be better if you try to explore the corner of the internal representation of the AI, essentially something that's far away.
First, as you said, that when you are dealing with a nonlinear control system, you observe that, I mean, your intuition is that the algorithm is not linearizing and then applying Kalman and so on. What if you ask, to deal with linear systems, controllability of linear systems? Of course, you can always say to the computer, listen, this is the Kalman condition, you check that, and the computer rank. No, but you don't say this. You simply ask, can this system be controlled?
Yeah.
Did you ever check what the computer does?
We never checked. So we never check to train on linear system and to evaluate a linear system. Yeah, of course, if we train on our usual nonlinear system and we evaluate the linear system, it's likely that it's going to do as it's trained to do and probably output the right answer. But maybe if we train on linear systems, it will behave completely differently. We haven't tried. That's a very good point. Yeah, that's interesting.
So will the computer understand the concept of bi-orthogonal, or I mean, we'll go into the eigenvectors of the matrix, try to.
Maybe I don't know if it will do it directly, but something that was in the previous course, the one I've already cited. There was
some kind of this external examples, right? Yeah.
Yes, they were a work where what was tried was to predict still the eigensystems of matrices, and when you're doing this, it appears that during training. So when you train these kind of models, it's really nice. What you have on the learning curve is essentially, so you try to go as high as you can, and it starts to be 0, then it jumps quite quickly. Then you have a threshold, then you jump again, and so it moves usually by jumps. And most of the time, we don't really know what those jumps is. It seems that the model understood something, but this something is hard to understand. For matrices, what apparently was the case, I wasn't an author of this paper, was that there are 2 jumps, and when you look at what happens, you see that before the first jump, well, the AI doesn't know anything, and after the first jump, the AI knows how to predict if the vectors are orthogonal or not. And after the second jump, it knows how to predict the amplitude. So this is one of the rare cases where the author was able to interpret what's going on, and where it's possible to give a meaning to what's going on. And here, definitely, the AI was learning orthogonality first, and then the amplitude of the vector. Now why, or I don't know, but that's definitely something that can be studied and is very interesting.
So a more philosophical question, but probably there is an easy answer. But I mean, to me, it's never clear, and oftentimes the students ask these kind of questions, right? Because it's very natural. It's okay, fine. So artificial intelligence, neural networks, we understand there is some universality. The theorem of universal approximation says you can reach everything by using this kind of architectures. Okay, we accept that. But why, when tackling specific applications like this one, for instance, that is about dynamical systems theory and Lyapunov functions, one starting from a ChatGPT or a large language model that has been built not at all to deal with this kind of problems, but rather to transform French into German?
Yeah, that's a very good question. So I think there's 2 parts of the answer. The first one is, for this kind of systems, we are using the architecture of the transformer, but we're not using a pre-trained transformer. So it's trained from scratch only on Lyapunov functions. Why using a transformer that was made, the architecture was made to translate from French to English or German to French. At the time, we thought that what these self-attention are doing is essentially trying to grasp the grammar behind the language that you're giving it. And maybe in math, if you can catch the grammar between the math, it's actually the mathematics behind. So that was the rationale behind. Now I think that people are more and more thinking that transformers are actually basic bricks of reasoning. They are actually the self-attention head that is looking behind to create links is actually the most basic reasoning entity that you can think of. So that would make sense for this kind of math problem to use this kind of model. Now, why on theorem proving we are using, or we will be now using models that have been pre-trained on English, French, and the internet to prove theorems? I think the answer here is mostly practical. When you train such a large language models, what you do at the very beginning of the training is essentially align the weights to understand that there is a structure, essentially, that even that this is a language. Independently of the language, you need to understand some kind of structure from the random weights. And this takes a lot of data and of training. And if your data is very expensive, you don't want to waste it to just make this beginning of alignment of the neural network. So it makes sense to train on something else that has a structure before using your valuable math data to train on top. I was very surprised because on the GPTF, they were trying to see what happens if we pre-train on English first, and they were getting much better results. And I was like, hey, what's going on? And indeed, one of my co-authors told me, yeah, it's not completely surprising because you just want to go from the very basic, completely random neural network to something that at least has some structure and grammar, and then you're going to keep training it with your specific one. Now, why? Now, it might not be the best option then to take something as pre-trained as ChatGPT or something like this. But because of the cost of the training and the small amount of data, it's still probably a very good option, or it's probably the best option related to the fact that we don't have that many data and that.
But do you think there is a theorem to be proved that in this on the architecture of these transformers there is sufficiently richness in this architecture so that you can represent classes of a given level of complexity, so that maybe, for instance, Lyapunov functions for polynomial ODEs belong to this level of complexity?
That's a very good question, and I would imagine that yes, but with two caveats. The first one is that those are very complicated architecture, as you know this, I think probably more than I do. And the second caveat is that I don't know exactly what is the state of the universal approximation theorem of the neural network, what the state of it, because I remember the one that everyone knows. It says you can always approximate any continuous function defined on the compact of Rn, but here we're not trying to approximate something that goes from Rn to Rn. We're trying to approximate something that goes from an infinite dimensional space to so it doesn't apply here. But I've seen recently some versions of the universal approximation theorem from something that goes from Banach space to Banach space. So that's
approximation of approximation.
Yes, approximation in some sense.
Yeah, it's a chain rule, right? Density,
right,
density
but
is density.
So I don't know what's the top of it and what would
maybe there is more than that. My feeling when I listen to lectures on this is that is density of density equal density, right? But okay, so I'm mistaken. But
really not
and then there is another thing. You see, I wonder whether actually there is even something more, because so here you say you don't expect 100% success, right? And then this is like, go back to numerical analysis. So what do we do in numerical analysis? We are trying to let the error go to 0 as the mesh size goes to 0. But assume I tell you, well, I want to approximate numerical analysis, I'm not interested on convergence because, well, we practice zero error. Well, nobody cares. I just need 100%, 1% error. Is there a numerical? I don't think there is numerical analysis for this.
No,
right?
no, there's no numerical.
And then I think here there is another difficulty related to this. It's not that probably we are not even talking about density, because if it were density, then we would have a frame.
No.
So we are talking about monsters that perform well 97%,
Yes.
but I don't know of any mathematics for this, right?
No, I don't think we will maybe even be.
So what, I mean, is there an example of PDE and numerical algorithms so that you get the correct solution 97% of the time? I don't think so.
No.
So you either have consistency and stability and then you have convergence, or, well, the algorithm is not consistent, then it doesn't make any sense, or it fails to be unstable, but then most probably solutions will go to infinity, but you will not get convergence 97% of the time.
No, this is very weird. There are two explanations. The one that is less satisfying is that those are monsters, those are approximate neural networks, and we don't really know how they're working. So this is the one that says essentially I don't know. And there's a second one that is, for these kind of problems, it might be that there's even a theoretical bound, because so I don't know for finding Laplace functions, maybe someone in online or here knows better than me this, but no, it might be that some of the problems we were studying might be NP complete, and in this case, if it is, and if P is different from NP, you have no way of finding a neural network that's going to converge, because 100% of the time, because if so, it would mean that you will have a polynomial algorithm, because those things are polynomial. But it might be that actually most of the cases, you know, if it were NP complete, it will tell you that you can't find a polynomial algorithm that will work 100% of the time. It might work 97% of the time. And there were some examples like this with the SAT problem, where so the SAT problem, you know, you can't have a polynomial algorithm. I mean, we believe you can have a polynomial algorithm that solved it in fine time, but you have people using transformers to solve the SAT problem, and it works, I don't know, 80% of the time, or 85% of the time, just because a problem that is a class of problem that is extremely hard might most of the time be actually feasible. There's no theoretical bound against this. So there might be something saying you can't reach 100%, but you can be close. But I think most of the explanation is we don't really know how these things are working. Especially because it's really hard to I don't know, to parameterize even those space. There are polynomials, okay, but non-polynomial space.
By the way, now taking the advantage that you are here, can you explain in simple words to all of us what attention mechanism is? Well, you mentioned it before, but maybe with some more details. So why is so relevant, and what is your mathematical, I mean, your interpretation from a mathematician?
From a math point of view, okay,
Yeah.
I'll go to the autoregressive part. So yeah. So the question is, you're here and you're trying to predict. Let's say you're trying to predict the next word or the next few words. It depends for the Laplace function. We try to output the entire Laplace function sometimes at once. But the question is, when you try to predict the next words, it's probably not the best sentence to illustrate it. You'd like to know which are the words before, the words that you already know, that you should pay attention to. For instance, if I go, I don't know, I went to the market with my wife, the next word, it's going to be she, it's not going to be he, just because you need to pay attention to the word before. So this is exactly what the attention mechanism is doing. So you can wonder, in mathematics, it does make sense, because if you want to predict the solution of something, it probably depends on what you have before in the equation. I mean, if you have x1 squared here, it's not the same as if you have x1 cubed. So you need to see. So the thing is going to be trying to see what are the pieces that you have are given in inputs before that you need to pay attention to. And so you have a number of attention heads that will point towards a specific word. I don't know, use 16 or something like this. And so that for each word, you're going to compute the attention, and so essentially what with a weight, what are the words I should pay attention to before.
So, for instance, if I read here, hope is a good thing, may be there. Okay, so now,
yeah,
assume I am the neural network and I am dealing with this to trying to guess what
the next one will be. You probably have to pay attention to thing, hope, and probably good as well. So that's what I'm saying. It's not probably the best sentence to illustrate it, but because you have at least 3 words that will probably have a non-negligible weight. But the fact that there's a here, it's probably not very relevant as soon as you already have the here. So it's probably going to have the attention will probably not point you to this.
No.
I mean, for instance, a good example would be, okay, you have a problem where an integer is involved. So with a high probability, you may use recursion or induction.
Yeah, for instance, if you're improving, you have you try to predict the next step. There are some important parts in the statement before, and you need to focus on the important part. For instance, if I don't know, if you've got an assumption that is rare, for instance, so I've got the statement and the assumptions. If one of them is pretty rare, you hope that your model is trained well enough to say, oh, wait, you should probably look at this. This is probably the important part. Now, when we try it on the Lyapunov function and try to interpret, so we could be able to say, this is, so we can give this to the system and say, okay, well, where are you looking at, essentially? What's the biggest weight you give to what in the system to predict the answer? And this is where it started to be very hard to interpret. I mean, they were saying, okay, I don't really I pay attention to this x5 that is at the end. I pay attention to this square here and to the cosine here. Hard to tell whether this is really the most important part.
Okay, the last question. We have 4 minutes left. Yeah, Siki.
I have a more detailed question. It's like you have mentioned is that data set and also the processing of the data set is very important. For example, I remember in your case when you encode the formulas, it's like you treat it like a tree and you use this, like the depth first search. So have you tried this, like if we use the west first search or something like that? Does that mean that you are, how to say, enlarging your data set? For example, I know like for images, we can just rotate them or split them.
Right, but if you rotate the image, you get something that still makes sense as an image. Here, if you start from like, I don't know, x2 to x1 sine power plus, you get something that doesn't make sense anymore. It's not the same vocabulary, so it would be hard to enrich the data set. Although, except from that, if you have something that will be, we're doing this because there's a perfect bijection between this and this. Essentially, you can go back with no uncertainty. It's slightly better than here, where the number of brackets you put depends on who you are, or there's a minimum amount, but it could be more. So putting it as a tree makes it extremely deterministic, and then this is just a way to enumerate the tree because it was already used in computer science. But you could find probably another way to enumerate the tree that would make it work. For instance, basic example, you would start from the top and go on the right first. I mean, obviously it's not going to change anything. So yeah, it will just change the way the transformer is seeing the language. But the very first step of the transformer is going to be to understand the language of what we're giving. So the very first step is looking at this and understand what is the form behind. And this is what the transformer learns at the very beginning. Like it's the very first thing for theorem proving. At the very beginning, you give it theorems, and very quickly the transformers outputs coherent name of theorems. So it looks at the form first, and then it learns more things. We had an interesting thing where at the very beginning we are using just GPT-like, so output the next step, and all the theorems carry the name. In Lean, the theorems carry the name that says exactly what they're doing, like A plus B equals something. And sometimes we're giving at the very beginning of the training, we're giving a statement saying show this. And the neural network will just output a theorem that has exactly the name needed to show the statement, but that doesn't exist, of course. So,
well, I think the attendance, the questions, the answers, the excitement was very obvious. So we thank you again very much.